Right, you'll have to tell me if you can't hear me at the back. Just shout or wave or something. So anyway, Mark has asked me to talk not about power amplifiers, for once in my life, but to talk about active crossovers, as he said with a book came out. There's a slight story behind that. My first ever active crossover design was 1979, the first one for commercial production. It was a bit of consultancy work I did. I still haven't been paid yet. But I understand the check is in the post. And that was it really for a long time. And then I did some more consultancy work a couple of years back, which got me back interested in the field of active crossovers. So I thought, well, I want to really get into this, really go into it in detail. And next thing you know, there's a great big fat book. Because I like to write it all down so I don't have to remember it. So anyway, let us get started. Because we have to stick fairly closely to an hour, I believe, for tape reasons. Right, that is the first slide. What do active crossovers do? Well, quite a lot of things. Well, in fact, any crossover has to do these things, but they're much easier to do if you do it in the active field. First of all, the obvious thing, you've got to split your audio spectrum into 2, 3, 4, 5 even bands, which is fairly straightforward. You can add equalization to get the drive unit response, to fit in with your crossover scheme. Now that's a little bit more complicated because you've got to try and work out how accurately you can get that, and how much variation you've got in your drive units. I mean, trying to equalize a drive unit to 0.1 of a dB, you really are wasting your time. That would, the next one will be a dB off. But so that's something that you have to think about quite carefully. You've got always got the possibility of enhancing the bass response by putting a hump in the low end. That sounds great. But you very soon find you need huge amounts of power and you need a drive unit with a very big movement possibility, a very big extension to get any sort of real enhancement at all. So it's not wise to put too much trust into that. The next thing is equalization again, or interaction between the drive unit and your enclosure. Now, I'm not really sure how deeply do loudspeaker design you all are. I mean, I'm not a loudspeaker designer, so, do please take that into account. But diffraction compensation is one thing you have to look at, where the low frequencies go around the side and around the back, but the high frequencies always come out towards the front, and therefore you've got a kind of a step in the response, which you can allow for, so long as you know your cabinet dimensions and so on. That should be fairly well fixed. You should be able to do quite a good job there. Now, the next thing, which is a bit trickier, is equalizing for the loudspeaker interaction with the room. Now, as you probably know, if you stick a loudspeaker in free space, traditionally on a 50-foot pole in the middle of a field, not ideal listening conditions really, but you've got their full space operation. Half space is when you stick it against a wall. So the LF tries to go around backwards, but it comes back forwards. So you get a better LF response. Quarter space, when you put it in a corner, say between the floor and the wall, then you more LF response again. And if you put it in the corner between two walls and a floor, then that's about as good as you can do in the average room. But of course that radically alters your LF response. And that isn't something that you can cope with very well with tone controls on your preamplifier. They're not normally designed for that sort of job. So some sort of switched or custom equalization on your crossover is a good idea. Though I'm not sure that anybody's actually done an active crossover with half space, quarter space switch on the front. Maybe they have, I don't know. I'm not aware of one. The next job is level correction for different drive unit sensitivities. Now, if you're doing that with a passive crossover, you've got a real problem because you've got to put a resistor or something like that, or maybe an auto transformer, in with your higher sensitivity unit. And you're throwing away power. Sometimes you've got to throw away a lot of power, and that's always a problem with passive crossovers. So, but of course, on an active crossover, it's extremely simple. Just got a little level control, a couple of resistors, and you can do whatever you like. And the final thing, and I'm sure Siegfried will agree with me here, is that it's really important to have time delays built into your crossover, which allow for the physical misalignment of the effective acoustic source in each loudspeaker. Because normally you've got your tweeter there, and the acoustic center of the LF unit will be further back. You know, unless you've got a stepped front on your loudspeaker enclosure, which brings in lots of extra problems, of course, because then you've got diffraction around the step, and and flat is really easier and cheaper to make. So what you need to do is to delay the signal going to your high frequency unit. Now that's very simple to do in an active crossover. In a passive crossover, it's very often not practical because you've got to make a passive all-pass filter, i.e. a filter that's got a phase shift but not an amplitude alteration. And once again, you're losing power. And to do it properly, in my view, you need something like a third order all-pass filter. Making those in passive components, you're going to lose any amount of power. And it's probably not a practical thing to attempt. So these are the things we're trying to do. Now, next one, please. Right, so what do you want your crossover to do? Well, this is roughly in what I would say is the accepted priority order. The thing that's most important is going to be almost always the flatness of the summoned frequency response on the axis. The assumption being that the guy who paid for the system is the guy who's sitting in the best place on the sofa, and he's the one who's on axis. And if you're off axis, well, hard luck. But so you prioritize the on-axis response. Probably the next most important thing is to have a sufficiently steep roll-off on your filters, because you don't want frequencies going to the wrong drive unit, because they've probably got a bad response outside the area they're supposed to be used in. They've probably got high distortion compared with the middle of their range. And of course, you've always got the problem that if a lot of low frequency stuff gets into your high frequency unit, you're going to destroy it. It is going to explode, perhaps. I have actually seen a cone do that, shoot across the room when somebody got that wrong. And the next thing is going back to the axis and off-axis bit, an acceptable polar response. So, I mean, you have to accept as a rule that the off-axis response isn't going to be so good. But you want it to be as good as possible. You don't want it to fall to hell when you're 10 degrees off. So that all comes into the design of the crossover because it's to do with the phase between the drive units. So, moving swiftly on, the phase response of it. Now, it would be great if loudspeakers, had a flat phase characteristic in the same way that electronic circuits do. But that's just not what happens. When you've got a crossover, you typically wind up with a phase that does this kind of thing. Even though the level is absolutely flat, you've got a phase that goes perhaps from 180 to minus 180 or something like that. And the question is that a problem? My view is that it's not really, because virtually all loudspeakers do that. A linear phase loudspeaker is something we're still trying to do, really. And lots of experiments demonstrate that you can't hear that. Very much tied up with that is the group delay behavior. So, in other words, some frequencies are going to be delayed more than others because of the phase response. Once again, is that a problem? And the answer, once again, from experiments seems to be it's not until it becomes gross. All of the figures on what you can hear tend to come from years ago from telephone systems, whereas what was acceptable as a group delay problem over a long telephone line. And, the same kind of thresholds do seem to obtain in hi-fi, because the human ear still working the same way. Anyway, next slide. Right, now I'm not, you'll be glad to know, going to plod through every possible advantage and disadvantage of active crossovers, because we'd be here for a while. But I'm just going to put them up on the screen and just talk a little bit about the most important ones. Probably the most important thing about an active crossover is you've got a great freedom of design. With a passive crossover, you've got all sorts of compromises because you can't afford to lose power. You want to try and keep the cost of the components down, because passive crossover components tend to be very expensive. And they get even more expensive when you go for a higher order crossover. Your classic, perhaps the most common crossover, is a second order one, which I'll talk more about that in a moment. And a lot of people feel that's not a steep enough slope between the two. You're getting LF in the high frequency unit and vice versa. So you can have barely as steep a slope as you like with an active crossover. Probably about up to eighth order is about as high as is practical, I would think, because you then run into trouble with component tolerances. And if you got to eighth order, I mean, it's DSP time. It really is. And you can make any kind of order you like, any filter you can think of. I mean, what I'm focusing on more is the analog implementation of active crossovers, because that's something that's a lot easier for many of us to do. You know, putting together a few op amps is one thing. You know, DSP programming is not for all of us. Right, now the second big advantage probably is quite a well-known one, that if you've got a multiple band crossover, then if one amplifier clips, it will clip only in its own band and it will not intermodulate across the whole audio spectrum. So that clipping tends to be really hard to hear by comparison with a full range clipping, and it's generally accepted that you could run a system 4 dBs louder for the same impairment if you're just about to hit clipping. That 4 dBs is a lot of power. You know, that is a very serious advantage. This is why invariably active crossover used for sound reinforcement at concerts and the like, always. And the third thing, I talked about time delays, and with an active crossover, your time delay is very easy to implement without losing massive amounts of power, which comes in at number 4. I'm not sure what happened about the space there. So those are probably the 3 big advantages, I would say. Now, I'm not going to go through all of these ones, but we could come back to them. If there's any particular point gets raised, we come back to them at the end, perhaps. Next. Right, this is the second screen of advantages. Now, in a lot of books, you'll see lists of pluses and minuses for active crossovers. I reckon there are 22 real advantages. That's the way I count them up. As I say, once again, I'm not going to go through this lot, but if you look at it, I think you can see they're all fairly serious advantages. Like no inductors, for example, is a big advantage, because they cost a lot of money. Okay, next slide. Right, now these are the illusory advantages. Now you often see these quoted in books as a reason why you should use active crossovers, but they're a bit bogus in my view. Firstly, they say, oh, well, there's less intermodulation and distortion in the power amplifiers. Now, as I just said, that's true if you're talking about clipping, you know, where you've got some obviously serious distortion going on. But if you're not clipping, then designing a power amplifier with very low distortion is these days not hard to do. You know, that is really not a good reason for going for active crossovers. Secondly, people always say, oh, well, you've got no danger of slew rate limiting in your low frequency and your medium frequency power amplifiers. Well, that's true, but you've got no danger of slew limiting in the high frequency power amplifier if you know what you're doing. It's very simple, once again, to design a power amplifier these days where slew limiting just is not going to happen in the real world. So that's, once again, a bit fake. Now, the next one is, people say, so there's a simpler loading for each power amplifier. Well, yeah, but the power amplifier doesn't have to understand the load. It just delivers volts and amps. You know, it's not sitting there thinking. You know, if you've got an impedance curve that looks like a cross-section through the Rocky Mountains, then that may be hard for you to understand, but the amplifier doesn't have to understand it, it just delivers the current. So that is, once again, I think a bit, well, more than a bit dubious. An even more dodgy one is saying that amplifier stability is easier to obtain because you never actually get pure capacitive loading, as you can do when you're driving a passive crossover. You know, it can go capacitive, could cause you trouble. But the answer to that is always, in my view, you just put a little inductor on the output of your amplifier, like everybody always does, or everybody always should, I might say. And it is always going to be stable. You will not be able to make it go mad by putting any capacitance that you can think of on the output. So number 4, also I disrespect. Now, number 5. People sometimes say, oh, well, it's cheaper to design a power amplifier that only has to handle a limited bandwidth. Well, it isn't. I mean, why would it be? You might be able to have slightly smaller power supply capacitors in the high frequency one, but most of the circuitry is the same. You know, you could make your high frequency power amplifier a bit smaller because there's a lot less energy up there, but I'll be coming back to that later on. But, you know, the saving is not big. Yeah, so that 5 has some truth in it, but it's not a lot. Now, the last one's a very dodgy one indeed. People say you can save money. I'm talking here about a situation where you have your power amplifier actually built into the loudspeaker box, which not perhaps a good idea, but I'll come to that later. And so they say, right, okay, there's no exposed terminals. You don't need to have short circuit protection on the amplifiers. And that will save you a few pennies until you get a voice coil that goes short circuit, and then everything catches fire. You've also got the problem, it makes it a bit iffy in the testing stage. You know, human beings make mistakes. So if you've got a power amplifier with no overload protection at all, you know, momentary short circuit while you're wiring it up and it's gone. So I always put short circuit protection on amplifiers. Okay, well that's six dodgy advantages. For the next one, please. Right, the disadvantages. Now these are real. And probably the most important is numbers 1 and 2, that you've got at least twice and probably 3 times the number of power amplifiers. You know, that's a lot of hardware. They start to, you know, pile up in the living room. You've got a lot more cabling to go with it. You know, and this can cause domestic friction. Believe me. Right. So going back to building the crossover into the loudspeaker, I mean, this is a real no-no because people want to choose their power amplifiers. And if you built the crossover into the speaker, then the amplifier's in there with it. And, you know, people won't believe that if you're good at designing loudspeakers, you're necessarily good at designing power amplifiers. And believe me, from some of the efforts I've seen, that's true. Really true. I've seen some shocking stuff done. So, I mean, my take on that is that you want to sell your active crossover as a pair with the loudspeakers and leave the gap in the middle for the power amplifier so people can put in any power amp they like. All they've got to do is get the gain get the gain correct, yeah, and then there are no other problems. Now, obviously, because you've got 3 times the number of power amplifiers, it's quite a lot more expensive. You know, the system is, you know, it's not cheap. Now, obviously, passive crossovers are not, as I said, they're more expensive to make than active ones. But that doesn't counteract the fact you've got a whole bunch of amplifiers there. So that's something you have to take seriously. Now, the active crossover has to be, you know, matched to the loudspeaker. I mean, you can't just buy a generic active crossover and just throw it in there and think everything will be right. And I mean, I'm well aware that in sound reinforcement applications, that is what they do in the sense that you buy a generic crossover and you tune the crossover frequencies and so on and so forth to match your system. But that is done by skilled and very experienced people with a lot of expensive test gear. And, you know, your average home user isn't going to be doing that. So what you basically have to do is say, here is an active crossover, it is fixed, and it is for this model loudspeaker. You know, and if you connect it to anything else, well, it might not be good. So, now, a real serious problem, I probably might have put this at number 1 actually, is that you've got your amplifiers, they're connected up now directly to the drive units. There is no crossover in the way. One of the worst things that a power amplifier can do is to have a DC offset fault. Typically the output goes bang up to one of the rails, and that can be extremely destructive to loudspeakers, obviously. And I have never designed yet a DC coupled power amplifier which didn't have offset protection in the form of a relay that opens when things go wrong. But that takes time. You've got to detect something's gone wrong. Usually there's some sort of low pass filter which inherently is not very quick. And you know, that works very well for protecting low frequency units. You know, you can pretty much say they're bulletproof. But now you've got a tweeter and a mid-range unit also directly connected to the amplifier. With a passive crossover, you've got a capacitor there. There's going to be at least one capacitor in the way, and that is going to stop an awful lot of low frequency energy getting through. So, you know, but a tweeter will go in an instant. It will go in the blink of an eye. I've seen it done more than once. And it's an interesting question. I mean, you would need to have a very fast DC offset reacting for that. Or, of course, one possibility is to put a great big capacitor in series with the HF unit. But then you're bringing back some of the disadvantages of passive crossovers then, because that's got to be a good part, it's going to be an expensive part, it's going to be a bulky part. So that's a bit of an unsolved problem, I would say, the vulnerability of tweeters in an active crossover system. Right, something to worry about a good deal less, unless you're into Class A in a serious way, is the greater power consumption you've got because you've got more amplifiers. For a Class B, Class AB, that's not going to make a lot of odds maybe, but if you're stuck on Class A, there's going to be some serious heat. Another, disadvantage, if you like, is the opposite of the advantage that you can do anything you like with an active crossover. The passive crossover is almost always fixed. Sometimes there's a vernier control, which affects the HF, but in general, it's fixed. You can't go around, getting it horribly wrong. Active crossover, particularly the ones you get in the sound reinforcement business, there's a big knob on the front, and you can change the crossover frequency by 20 to 1 in an instant, which might not be a good thing. Right, and the final thing, which to think about, is that an active crossover is putting electronics in the signal path that otherwise would not be there. There is going to be some signal degradation. The question is, how much can you put up with? I'm going to be talking later about how little you can mangle the signal, but it is something to always think about. That is an extra thing in the signal path. Right, next please. Right, you're ahead of me. Okay, having just gone very quickly through the advantages and otherwise of active crossovers, I just want to have a relatively short look at how they work. I mean, in this talk, I'm trying to provide something for everybody, whether you're a crossover expert, or whether you know nothing about them. So if this is all obvious to you, please bear with me for a little bit, because at the end I'm going to tell you what I believe is some new stuff. So this is the sort of thing that crops up in correspondence columns in magazines over and over again. And they say, oh yeah, here's your second order filter. You've got the second order Butterworth filter, a maximally flat one, in each path. And then it's always assumed that the sum is absolutely linear sum in the air out there. I mean, you're not going to be loud enough to make the air non-linear unless you've got a rocket or something like that. I believe that happens with the space shuttle main engines, or used to. The air would actually go non-linear, which is why you get that kind of crackling effect, which is not really what you'd expect. So, that looks, you might think, yes, that looks feasible. You've got the same crossover frequency in the two filters, so they'll both be 3 dBs down at the same point. What could possibly go wrong? Next slide. This is a typical implementation of it. It's your standard Salon and Key filter. These are the correct component values for a 1 kilohertz crossover, and it's Butterworth, so it's maximally flat. The Q is 1/√2 for the filter in both cases. These things, by the way, are phase spikes to show you that that when the filter isn't actually doing anything, it is in phase. Right, next. So you implement that, and you say, what could possibly go wrong? And the answer is, this is what happens. You get, when you sum the two channels together, and you get this notch as deep as the Grand Canyon, right at the crossover frequency. Now that, surprisingly, doesn't sound quite as bad as you might think, because it's quite a narrow notch, but it's not exactly a good move in terms of getting a flat response. So what on earth has gone wrong? Next one. What's gone wrong is that you've not allowed for the phase shift in the filters. And that phase shift is 90 degrees in one filter, minus 90 in the other, 180. You've got complete cancellation at the crossover frequency. So you think, right, well, let's invert one channel. So you phase invert it, and now you get something a bit more like a crossover. You've got a peak of, I believe it's 3 dBs there. This, by the way, these are that's the low frequency channel, that's the high frequency channel there. And you sum these together and you get this little hump. Now is that better than having a great big notch? Well, it looks better, but it might actually sound worse. So what on earth can we do about that? Next. Right, what you can do about that is to say, right, we don't have to have the cutoff frequencies of the filters at the same frequency. They can be offset. And if you do that with this Butterworth crossover, you find that the magic number is 1.3. You increase the high frequency crossover by 1.3 times, and you reduce the low frequency crossover filter cutoff by 1/1.3. So you're pulling apart the two cutoff frequencies, And this is what you get. When you sum them phase inverted, I hasten to add, you get this curve here, which it's not totally flat, as you can see, but that frequency offset gives you the minimum wobble. It gives you an equal up and down of about 0.45 dBs, which I think you'll agree is a considerable improvement on having a 3 dB hump. I mean, 0.45 dBs, that could get lost in your the response of your drive units quite easily, and can probably be allowed for an equalization or whatever.
It's pretty hard for someone to hear, isn't it?
I would have thought that was probably impossible to hear, but it's very dangerous to make dogmatic statements about what people can hear. So anyway, we just noticed 0.45. If you go back to the first version where it's not phase inverted, you might wonder what's happened. Well, you've still got, no, you still stay with that slide. That's it, yeah. This is what you get. You've still got a big cancellation, it's just it doesn't go right down to minus infinity. So that's still useless, basically. But if you're going with second order Butterworth, that's the best you can do with frequency offsetting. That's a very powerful technique in crossover design, which we'll come back to later. Okay, right, next one. Right, and now Siegfried, I know, is sitting just over there. Now, the great thing about the Linkwitz-Riley crossover is that it sums to flat. This is my attempt at a second order Linkwitz-Riley crossover. I'm sure Siegfried will tell me if I've got it wrong. What you basically do is instead of a Q of 0.707 for your filters, you have a Q of 0.5, so the roll-off is that much slower. And that is done just by changing the values of the resistors in this case and of the capacitors in this case. So very simple. It's beautifully simple to design because, as you can see, the components are all the same value. Okay, next. And so what happens with that? Well, if you have it phase inverted, like we did last time, then it is perfectly flat. It is this line here. If you don't phase invert it, you still get a hell of a notch, which is not much use to man nor beast. Now, the important thing about the Linkwitz-Riley system is that it's minus 6 dBs at the crossover point and not minus 3 because of the much lower Q of the filters. So you see, we have now got an absolutely flat response, which is excellent. But is second order steep enough? I mean, a lot of people would say it wasn't. That was not going to keep the LF out of the HF and vice versa well enough. So next one. So your fourth order Linkwitz-Riley, which is sometimes called a Butterworth squared filter because you make it by having two Butterworth maximally flat filters in series. They're both 1 kilohertz here and both got a Q of 0.707, 1 over root 2, and the same applies in the LF path here. And once again, you sum it linearly in the air there. Next. And magic. Absolutely flat, again, as the Linkwitz crossovers are. Minus 6 dBs at the crossover point, but if you recall the previous slides, this is a lot steeper, obviously, because it's a fourth order filter. And that is, I think, reckoned by probably the majority of people to be the way to go with a crossover. You know, that is the one. If you're going to try and come up with something new, that's what you've got to beat. So, okay, move on. Right, what I want to talk about now, I mean, I've gone through some, stuff that is pretty standard stuff. I've been doing quite a bit of work on active crossovers recently, sometimes for consultancy clients, sometimes just for my own amusement. And there's some things here to think about which I think are all relatively new. These are all in the book I wrote, by the way. So first of all, my old friend Neville Teal came up with this remarkable thing called the NTM, which stands for the Neville Teal method, crossover, a trademark, you'll note. So that is one thing I'm about to talk about. Another interesting thing is the delay filters. I will explain that more at the time. But there are ways to make all-pass filters which are more economical than just stringing lots of first-order ones together. Right. Next, mixed capacitor filters. Well, I'll leave that enigmatic for the time being, but you will see what I mean later. Elevated crossover levels. Now, the idea here is that you can run your crossover at a higher level than you might think, without any danger of clipping. which means that effectively its noise performance is better. The signal-to-noise ratio is better. In the same way, everybody knows, I think, you get a much less level in the HF path, so you can push that level up even more, which I will explain more about in a moment. And while you're worrying about noise in your crossover, one of the things that you find is that probably the noisiest part of it is the balanced input amplifier, which you might not expect. So that is one little bit of circuitry, which then splits into your 3 or 4 paths. So if you can make an improvement to that little bit of circuitry, that ripples through the whole business, and the whole thing becomes that much quieter. So I'll be talking a little bit about that. And I'll demonstrate how much that improves the overall noise performance. Okay, right. So the Neville-Teal notch crossover. Now this is I don't know, how many people there have heard of this one? Anybody? Right, not many. Okay. It is very clever. Neville is a very clever guy. Basically, what its characteristics are, it's a notch crossover. In other words, the frequency response doesn't just do a roll-off, like the filters we just looked at, but there's a notch in it, so it goes right down, comes back up again, and then goes down and keeps going down. Now, you'd think that fitting these notches together to get a flat response is going to be really, really hard to do, and it's going to have to be fantastically precise. But the beauty of the NTM is that it's not actually the case. It is quite straightforward to get it to some flat within 0.05 of a dB, which as far as we're concerned is flat. You can make it as a 6th order filter or as an 8th order. What you can't do, as far as I'm aware at the moment, is have such a thing as a 4th order NTM filter. It's just not mathematically possible. If you want to dig into this, it was published in 2 places and 2 places only. Because this is a proprietary method, it's patented. I'm not aware anybody's actually exploited it or taken out a license, but this is proprietary stuff, and I've had to get permission to tell you about this and to make it public. It is basically the patent is assigned to Techstream Putty, whatever that means, in Australia. And if you want to do anything with this, you would have to talk to them. But the references to look up, feel free to take a picture of the screen. But I will also be putting this, the PowerPoint thing here on my website when I get back home, so you don't have to memorize anything. There was the JES paper, loudspeaker crossovers with notch responses, it was back in 2000, and the corresponding US patent is this number here. Now I've got to tell you that both of those, both the article and the patent, are not an easy read. They are really uphill work, I found it anyway. For me, but feel free to dig into it and see what you make of it. But I have explained it, I hope, much more clearly in the book. So, next please. Right, and this is the NTM crossover in action. Each filter path, this is the high frequency filter, and this is the low frequency filter. Now, you're probably saying, well, that's not much of a notch, really. That's a pretty feeble notch. But the thing is that when you've got a crossover, the contribution of, say, a signal down here to the total response is very, very small indeed. So the fact that that notch doesn't plunge down to minus heaven knows what is really not of any significance at all. What is important is that you've got this kind of step here. And you'll note that you've got a slope here which becomes much less down there. But when the slope becomes less, you're further out, you're further away from the crossover point, you're right down at minus 35, and once again the contribution of that to energy into the loudspeakers is very, very small. Okay, now you can't see it very well here, but there's a line there which indicates it's something to flat. Next please. Right, so we zoom in mightily, so you've got 1 dB minus 1 dB, and this is what you get. The 2 filters, the HF filter there and the LF filter there, have this response with this carefully controlled little peak there. And now if you sum those 2 together, you get this green line here, which I hope you can see. Now, I will be honest, I'm not sure I've got that quite right. My understanding is that this is supposed to sum to exactly flat, But what I did with this, I didn't do the mathematics. I simulated it with real op-amps, with 5532s. And that is what I got. You know, the error there is extremely small. It's less than 1/10 of a dB, which is probably negligible for crossover use. But whether that is due to bandwidth limitations in the op-amps or something else, right at the moment I can't tell you. But as you can see, it's not exactly significant. But the fact it's asymmetrical and it's not the same both sides makes me think that I have screwed up there somewhere. I wouldn't be surprised. Okay, if you'd like to go to the next one. So how does it work? What you've got in an NTM crossover, you have a second order filter here, which is somewhat underdamped. I mean, the Q is, I'm not sure off the top of my head, something like 1 maybe. You have a filter which gives you a low pass notch. And so you've got your notch here, and it's a low pass notch because your 0 dB is along here, but on the high frequency side of the notch, you're down. At it'll level out, but it's leveling out to something that's lower than this end, so that counts as a low pass notch filter. If it was the other way around, it would be called a high pass notch filter. Because what you normally expect a notch filter to do is be symmetrical and go 0 dBs right down and back up to 0. No reason for that to happen. It's perfectly possible to make them so they do this to any level you want. Not that easy always, but it's perfectly possible. Right, now so you've got those two filters there. You've then got two first order filters. In other words, it's just an RC roll-off, just an R and a C, 6 dBs per octave, absolutely no variables there except for the frequency at which it's minus 3 dB. It's got no Q or anything because you've only got one variable. So if you sum these together, you get that rather funny kind of curve with a little step in it that we saw in the previous slide. Okay, next one. So how do you make it? You make it like this. Your low pass notch filter for the LF path, second order low pass filter with a high Q, so it peaks there, and your two first order low pass filters, minus 6 dBs per octave each one. And in the HF path, exactly the opposite. You've got a high pass notch filter, so that is the 0 dB part, and that is minus 10 or minus 5, whatever. High pass filter once again peaking, and two CR minus 6 dBs per octave first order filters. So that's what you've got to build. Next, please. And that is one way to do it. This is my version. This is not taken from the patent. This is not taken from Neville's article. This is my interpretation of it. This is the notch filter, the low pass notch. That's a bridge T circuit. It is not a simple thing to design. It's a pain in the neck. Thank God for simulators. I'm just going to twiddle it till I get it right. Sometimes you have to do that. Now you've got your peaking low pass filter. So the Q actually here is 1.6. Now that's quite high for a Salon key filter, but it's not high enough to give you any really serious performance problems. You then have your first order low pass, and there's the second one. But of course you've got to put a buffer stage in between them, because otherwise this one will load that one, and you will not get the response you want. You won't get two separate minus 6 dB per octave roll-offs. Right. Now looking at the high frequency path, you've got a high pass notch, which you'll note is similar, but not quite the same. The values are all different, as you might expect, though, but the salient change in the configuration is that this resistor here is now there. Now that to me is not an intuitive circuit. I mean, I can't look at that and say, hey, that's a high pass notch, but trust me, it does work. After that, you've got the second order filter, once again peaking, and the peaking being arranged by the ratio of these two resistors here, I should say, which is, as you can see, that's quite a hefty ratio. And likewise with these capacitors, you've got 200 nanofarads there and 22 there, which is not the sort of thing you very often see in a Salon key filter. A Q of 1.6 is probably about as far as you want to push that configuration. You know, if you want, you'd have to use something more sophisticated if you wanted a higher Q. Right, then the first order high pass and the second first order high pass, once again buffered from each other so you get the correct response. Okay, this is the original version. This follows the block diagrams and the general theoretical thing of Neville's approach. So next one. Right. So naturally, being me, I won't leave well enough alone. I always want to try and improve it a bit. And this is my attempt. If we could just go back to the last slide for a second. Yeah, stick with that one. Now, you may have noticed that there's no buffering on the outputs here. In the real world, that is going to have to drive something, and unless it's a very high impedance, it is going to affect the response of this final 6 dB's roll-off. So that is, in its sense, is an incomplete circuit. There should be another buffer just the other side there, but I thought if I made it any smaller, you wouldn't be able to read it. So next, please. So, simplified version. You've got a second-order low-pass filter now, instead of 2 first-order filters. If you make that with a Q of 0.5, then that is exactly equivalent to 2 first-order filters, one after the other, and properly buffered from each other. And you've saved an op-amp, basically. So that is my homage to Neville, as it were. That is my version of his crossover. I have not actually put it into a loudspeaker, I must tell you. I'm not a loudspeaker designer. But I offer that to the world, if they want to try that as my interpretation of what Neville was doing. It's a very interesting idea. As you saw, it has very sharp roll-offs because of the notch, sharper than you would get with a 4th order Linkwitz. So the question is that worth the extra hardware? Good question. I don't know. Okay, next, please. Right, delay filters. Now, Siegfried said that a crossover without delay compensation is marginally usable, and for what it's worth, I wholly agree. Now, the classic way to do it is with a first-order all-pass filter. These rather simple and unassuming little circuits, which are actually a bit more complicated than they look. But what I have done here is you've got version A and version B, and they basically do exactly the same thing, except that version B does it with a 180-degree phase shift compared with A. Now that's a phase inversion. That may be convenient in your overall block diagram. It may not. But these are the options. Interestingly, they have subtly different distortion characteristics. But I can't really get into that, even if you want me to, for lack of time. Now, for an 80 microsecond delay, which is, I would say, something like the average delay you're going to need between a tweeter and a mid-range unit, at a nice round number anyway, then your figure for R1 there is 1820 ohms, or there 1820 ohms with a 22 nanofarad capacitor, so they're nice practical values. And that corresponds to having the acoustic center of your mid 22 millimeters behind the tweeter. And that 22 millimeters is very carefully chosen to give you the round figure of 80 microseconds. So, next please. This is what you get. You've got an 80 micro. This is a graph of the group delay versus the frequency. For our purposes, group delay is just delay of the signal. And as you can see, just 80 microseconds, that's what we want. But as the frequency goes up, it rolls off fairly fast. And so it's down 10% at 2.5 kilohertz, long before we've even got to the crossover frequency. And it's down 50% at 9.3. That is going to completely mess up your delay compensation. That is just not flat enough. What we want is something that goes along here, horizontally. And that simple little circuit is just, that's as close as you can get. And then there are no other variables. If it's 80 microseconds, then it's going to roll off, and it will always be 10% down at 2.5 K. That's it. There are no other variables you can tweak. Next, please. So, this is a circuit which is a lot less well known than the first order one. This is a second order all pass filter. So the phase changes at twice the rate as the frequency changes. And you get correspondingly greater group delay. Now, this has been carefully designed to give you an 80 microsecond delay again. And it is now down 10% at 4.8 kilohertz instead of 2.5. So we've gained almost a 2-to-1 improvement, albeit using a bit more hardware. Now, you might be saying, well, how on earth is that an all-pass filter? Which is a very good question. This is another very non-intuitive circuit as far as I'm concerned. What you've got here is a bandpass filter. It's a very standard multiple feedback bandpass filter. And you run that into this summing stage here, along with a sample of the input. And if you arrange it so the output is the input minus twice the output of the bandpass filter, and that is arranged by the values of these resistors here, miraculously, and I think it's far from obvious, you get a flat response and an second order all pass filter. It is, as I say, that is just so non-intuitive to me. But believe me, it works. And just as a reference on the noise, this circuit generates minus 99.6 dBu if you make it out of 5532s. But just as a side comment. So next, please. Right, higher order filters. We've just looked at the first order and the second order. This is the first order, and as you can see, it rolls off horribly early. 80 microseconds is along there. And there's a line here, I'm not sure if you can see it, at 72 microseconds, which represents 10% down. Now, you probably think, well, how accurate does it have to be? That's a good question, because an inaccuracy in the group delay, it turns into an inaccuracy in the amplitude response. It will no longer sum exactly to flat. But as far as I can work out, so long as you're 10% down, well clear of your crossover frequency, at least an octave away, an octave above it in this case, then it's probably going to be negligible effect on the summed amplitude response compared with your tolerances in your drivers and so on. So, the way this works is, every time you increase the order of the all-pass filter, you get a constant increase in the bandwidth. So the increase from 1 to 2 is actually the same as from 2 to 3. And the only reason it looks like it's closing up is because we've got the traditional logarithmic frequency scale at the bottom. But, hearing's a logarithmic business, so effectively, it's a law of diminishing returns. The higher order filter, the steps get less and less. And I reckon that probably a third order filter, which is this one here, is probably the optimal way to go. Next, please. So that is a third order all pass filter, which you may not have seen before. What it has is the second order all pass filter that we just looked at, and that is followed by the first order all pass filter we looked at before. And so the total, it adds up in the same way as filter orders for amplitude response. That adds up, if you do it right, to a third order all pass filter. I don't expect you to have remembered the component values, but they are quite different in this bit. And you may note that the resistors here are different as well. And the noise is different too. Interesting, we had minus 99.6 from our second order one. This, because of the different component values, is quite a lot quieter, at minus 103. And even when you add on the extra stage, you're still significantly quieter than your second order filter. So the third order filter is not only flatter for longer, because it's now 10% down at 12.7K, but it's also quieter as well. So it's got a lot going for it. To my mind, this is the way to go on delay filters. Okay, next. Right, now the next topic is capacitor distortion. When I first built myself an active crossover, I was appalled to discover that capacitors distort, because this is something that people don't talk about a lot. So this is, now some capacitors I should say, some capacitors distort, some don't. Basically polystyrene ones are linear, they are distortion free. Polypropylene are distortion free, but they tend to be bulky and expensive. And so the ones everybody uses tend to be polyester, which are not too good from the point of view of distortion, as I will now show you. Right, this is the second order Butterworth low pass filter at 500 Hertz. A classic roll off there, minus 3, about 500. Next. And this is what happens if you measure the distortion. First of all, assume you've got your nice expensive polypropylene caps in it. Then this along here is actual distortion. As you can see, it's extremely low. It's basically the distortion of a 5532 op amp that's not being pushed too hard. This bit here is when the filter starts to roll off and the noise level comes up. So this isn't distortion going up. This is the relative noise level going up because the amplitude is going down. So, this is what you would get from what is, in a sense, your perfect filter. You now think, polypropylene, expensive. We'll use polyester caps, which probably cost about a tenth. And then things are not so good. You get this peak of distortion. That's basically third harmonic distortion, so it's not exactly euphonic. And as you can see, it gets up to 0025. It is far greater than the distortion of the op-amp. And interestingly, it peaks not at the cutover frequency, which you might expect, the cutoff frequency, but at 200 hertz. Now, why that is the case, I don't know. Work in progress. Something about the filter is as bad as possible at 200 hertz. Anyway, so this is done at 10 volts RMS, I should say. That's quite a high level. But that is, not that far above the level we might want to use in active crossover, as I will tell you. Next. Right, now the interesting thing about this, and this remains a bit of a mystery, but once again, work in progress, is that you don't have to make all the capacitors polypropylene. If you make that filter there, and you put the polypropylene one there, and you put a couple of cheap polyesters here, that too is distortion-free. The distortion is centered on this capacitor here and not these two. Now, once again, my intuition fails on that one. I don't know why that is. I'm going to find out. But, you could save quite a bit of money in an active crossover, because probably the polypropylene caps will be the most expensive part of it. They will cost you more than the op-amps, more than all the other components. If you've got something like a 470 nanofarad polypropylene, that's an expensive part. That's going to cost you, perhaps, I don't know what the cost would be here, $1 maybe, something like that. Anyway, the high-pass version is also interesting. There you have to put the good capacitor in the front, and you put the bad capacitor in the back. And once again, that has extremely low distortion. Yeah? That's right, yeah, the standard polypropylenes out of the catalogue. And not special ones in any way. Any sort of polypropylene will do, as far as I can know. I've measured lots of different sorts, and they all seem to be completely distortion-free. So that is, at the moment, an enigma. That is work in progress. It's potentially almost halves the cost of a complicated crossover, so it could be quite important. Next, please. Right, okay, that's it on capacitor distortion. This is about noise. Now, I'm not sure how much of this you can read at the back, but I will do my best. Okay, right, yep. So, we're assuming this signal path here that the internal level is 0 dBu, which is perhaps sort of common kind of level. So a lot of systems use -2. And if you make certain assumptions about the noise, like your input amplifier is -100 dBu, all the filters are -85, you're just looking at one path here, of course. Then you will add this up and you get -84.9 at the output. And of course, -84.9 going into your power amplifier, which is not very low, really. That's not my idea of low noise. So you think, what can we do? So, and then you think, there's absolutely no reason why you can't run the crossover at a higher level than 0 dBu, assuming it's connected directly to the power amp, because the power amplifier will always clip first. And you could probably put this higher. And this is assuming you haven't got a level control, which somebody's going to maladjust wildly. So now you've got the same noise level there, same noise level there of -85, and it adds up to -84.2 here. But then you put in a passive attenuator to get your +8 back to 0, and that of course attenuates the noise as well. So you now got -92.5 instead of -84.9, and pretty much at zero cost, you've got a signal-to-noise ratio improvement of 7.6 dBs, which is not the sort of thing you get every day. So, I mean, that does assume that you're not allowing for someone to maladjust a level control here. I'm assuming that if there is a level control, it's just a little trim with a couple of dBs each way. Yeah?
Why are you putting the attenuator at the output of the crossover instead of the input of the power amp?
Well, as you can see, they're very low resistor values. I mean, the output impedance is something like 180 ohms or something. You need quite a lot of cable to get a roll-off there. But the thing is, I mean, if you built it into the power amplifier, then it's a specialized power amplifier that you can't use for general purposes. So there is, a lot of incentive to put it in the crossover. Putting it in the amplifier has got the extra advantage, of course, that you equally attenuate any noise that's picked up on the cable. Any ground noise in the earth, anything like that, is equally attenuated. But as I say, that does it means you've got a specialized power amplifier that you really cannot use for anything else. It'll have a very low input impedance, for one thing. It's good.
You could put in the cable connector on the amp end.
Yes, indeed. I mean,
Specialized cable, but amp
oh yeah, quite. And this you will find is my solution in the book. In fact, I'm slightly ahead of you. It's a very good point. Yes, a specialized cable is fine. A specialized power amplifier is not a viable product. Okay, next. Right. So we've implemented an elevator crossover level. We know it's not going to clip. As far as we can tell, we've lost nothing. Assuming the distortion performance of the op-amps is good, then the distortion, won't be a problem. So what else can you do? You think, well, everybody knows that there's less energy in the high frequency end of the audio spectrum. But actually getting figures on that is very difficult. There is only one article that I'm aware of that's ever been published which gives you that information in a sound form, and it did need quite a bit of manipulation to turn it into this, which is basically a graph of the relative levels against frequency, and this is just sort of notional LF, mid, HF crossover bands. So you can see up here, you've got the highest levels there at the top of the LF, and you've also got high levels here. Basically you can't afford to elevate the level of the mid compared with the LF, but you can elevate the level of the HF, because the highest levels there are something like that comes out at about minus 37 as opposed to minus 31. So you could whack up the level on the HF path by another 6 dBs, and you would still be equally free from clipping.
As far as speaker cables running all the way from the speaker all the way back to your crossover, do you prefer running a 3-line rather than a 2 to reduce hum and just better sound?
Balanced, I think you mean.
Pardon me?
You mean balanced, right?
Yeah.
What, a balanced drive to the loudspeaker?
Well,
No,
balance.
input.
Oh, what, to the input of the crossover?
Pardon me?
Sorry, you're putting a balanced cable on the input to the crossover, or
Running
to the
all way
amplifier?
through the whole process.
Well,
Lines.
I'm not aware you can get balanced loudspeakers, unless they've got transformers in them or something. But I mean, I would certainly advocate running balanced between the active crossover and the power amp, definitely. In fact, whenever you can do it. I mean, there's lots of reason, every reason to do active and balanced if you can. Yeah?
I have a foundational question. I am confused from the get-go. This is, and I'm newbie, so sorry about this. The title is Active Crossovers, but yet we're talking about resistors and capacitors.
Yeah.
Is this because of the mathematical methods that the signal processor use, or in that
Well, I mean,
analogies to the physical world?
it's not so much that. There's no sort of direct analogy. But you've got to use resistors and capacitors to make an active crossover. Unless, of course, you're going into the DSP domain.
He's confused. Yeah. He's confused.
So, you're going to be using those resistors and capacitors, and resistors are not a problem. I'm not saying resistors are perfectly linear, but they're a lot better than capacitors.
What are your opinions between DSP and analog?
Sorry?
What would your opinion of DSP versus analog crossover?
Well, I would say that, supposing you've got an analog signal to start with, then you've got to convert it to digital, do your DSP, and then convert it back. Now, I don't pretend to be completely up to date with the modern converter technology. I'm probably a bit behindhand, but you're going to get some compromise on noise and distortion in doing that. I believe, in fact, I'm pretty certain that you can get a better performance by going analog all the way. If you're in digital to start with, of course, if you're coming off a digital source, that's a different question, totally different. What I've done in my book is basically tell you what filters you want to do. I then say, okay, it's up to you now whether you go DSP or whether you go analog. And I will show you how to do the analog bit because that's specialized knowledge and it's not that common. But the DSP stuff, you need a DSP textbook really. I can't write a DSP textbook in a book on crossovers. Are you ready? Okay, right. So, there we go. once again, I'll be putting this on my website. But that is well worth looking up, the Greener and Eggers paper. It's the only one I know that gives this extremely useful information. Okay, next slide, please. Right, this is an implementation of that. Once again, I'm not sure how visible that is at the back of the room. That was about as big as I could. I don't think you can zoom that up. So, right, elevated crossover levels. What I'm doing here is I'm assuming. Can you zoom in a bit? That's it. That's fine. I'm assuming 0 dBu coming in, and I'm assuming that we're pushing it up to 3 volts RMS. That will give us a definite margin of safety. I mean, your power amplifier will clip at least, I would think, 10 dBs before, depending on the sensitivity of power amp, of course. So, obviously it's important to get the gain in right at the front end, because you want to get the level up as fast as you can, so there aren't any stages degrading it. And of course, if you do it here, you only have to do it once. If you wanted to amplify it later than that, you'd have to do it 3 times, or 6 times in a stereo system. And I was talking just now about having extra gain in your high frequency path, and that is implemented here. It's quite straightforward to make a filter which has got 6 dBs of gain and still has the exact Butterworth response that's identical to this one here, which is 0 dBs gain. So just going through this is a complete crossover. This is sort of a generic 4th order Linkwitz Riley, I suppose you could say. Balanced input, low noise, which is a topic in itself. The 2 Butterworth filters, which make up the high frequency path, and a 3rd order all pass filter there, with the sort we just looked at, with an 80 microsecond delay. And this is probably completely invisible to you, but there's 6 volts RMS there, nominal, not real, because the level is lower, and it comes out, I'm assuming at plus 2.2. This here is a trimmed network, which gives you plus 3 minus 6 dBs, and the assumption being you're going to at least want to trim for variations in your drive units. It's not a volume control. It's just for trimming out production tolerances, essentially. Right, if you can, that's it. Fine, thanks. In the mid path, of course, you've got 2 sets of filters. You've got the high pass, 2 high pass Butterworth filters, and 2 low pass Butterworth filters. These all have a gain of 0 dBs. You then have your 3rd order time delay filter. That is a 400 microsecond delay instead of 80, because the assumption is you've got a bigger spatial difference between the mid acoustic center and the acoustic center of the bass unit, which I'm not sure quite how many millimeters I assumed, but I worked it out carefully, so it came out at exactly 400 microseconds for this example. So the crossover frequencies are 3K and 400 hertz, which is just average values, I would say. There's nothing actually magical about them. Right, and now there's your low pass. 2 low pass things here in the low frequency path. And there is, of course, no delay filter, because you've done your relative delays here and here, so this one goes straight through. It's the one that is not delayed. And there is a fixed attenuator there, which brings your level back down and reduces the noise, because you've got a relative tweak there and a relative tweak there, so you can simplify it there. Right. So.
Question.
Yep.
Why is the tweeter not 480 milliseconds?
Because the difference between the acoustic center of the tweeter and the mid is going to be a lot smaller than the difference between the acoustic center of the mid and the LF, just because the LF is bigger, and it's going to have its cone set further back. So that's just a sort of, it's just an average kind of a value. I mean, it varies obviously with speaker unit and so on.
Did you relate the mid by 400?
That's right, with relative to the LF, yeah.
So your tweeter is just a delay between that and the mid.
That's right. The assumption being
the assumption is that
the LF is gone by then.
It's 480 to your lower frequency.
Well, the assumption there is that by the time you get up to that kind of frequency where that matters, the contribution from the LF path will be negligible. It's a 4th order filter, 24 dBs per octave. There's going to be very little there. So there's the 2 moves there. There's the balanced input amplifier with a gain of 4 times, or 12 dBs, and there's the extra 6 dBs for your high pass path there. Okay, next one.
Do you convert back to balanced on the way up?
Not in this case, no. This is an unbalanced output. I mean, I'm kind of assuming there'll be a balanced input on the power amp. It's probably the place to have it, because it's the other end of the cable. Then that's just an assumption. You know, this is not set in stone. This is basically examples and sort of to show you how it can work. Right. So this is the first attempt at the low noise balanced input. There's your standard differential amplifier here. Now, if you're going to make that work alone, then you're going to have these resistors are going to be about 10K. And that is quite a noisy stage when you've got 10K resistors. So what I do, generally as a standard practice, is put a couple of buffers in here. So I can drop the values of these resistors. So that's 560 there and 2K2 there. And that reduces the noise of this stage by, I think it's about 7 dBs off the top of my head. I've shown the full Monty here on the input stage. You've got DC blocking, you've got EMC filter, and these, of course, are just the bias resistors to bias the buffers. And so you wind up with a noise level here of minus 100.9 dBu. So you then go into the bandwidth definition filter, which is something else I always tend to include, which defines the roll-off at the bottom and the roll-off at the top, rather than just relying on sort of accumulating losses, which is never sound. You've got here a third-order subsonic filter, a third-order high pass, and you've got here a second-order low pass. And you can see they've been cunningly jammed together in the same stage. So you've only got one op-amp to create noise, and saves money, saves power, saves everything. And that will only work for something like this sort of filter where the cutoff frequencies are very far apart. You know, this I think is 20 hertz, and this is, I think I set it to 50 kilohertz, I'm not sure. But they do need to be octave upon octave apart, otherwise it'll mess up the response. So, noise output from this stage here, minus 100.9. The noise output from this one, remarkably, is slightly less. And that is, of course, because of the filtering action. You've actually filtered out some of the noise coming out of here. I'm assuming a 22 kilohertz bandwidth for the noise measurement. But even so, this stage here still produces some noise. So that is why that looks the wrong way around. And I assure you they are correct. Next. Right. Now, supposing you said, well, I don't want to do it that such a complicated way. I just want to have a plain balanced input. Then you'd have to do it like this. Assuming your input impedance was going to be the same at about 47K as a minimum, then you've got to use 68K resistors here, 270K resistors here to get the gain of 12 dBs. And the noise output is minus 86.6. I mean, these obviously, this is one-off measurements with just a few samples of op-amps, but 5532s don't vary much on their noise. And that is 14.3 dBs worse than the first version. So that is why I go to the extra complication. You know, that's a serious amount of noise. Next. So this is the overall noise performance of the block diagram I showed you using 5532s all the way through. And you attenuate the noise at the output with your passive attenuators. And these, I think you would agree, are fairly low noise levels coming out of a piece of equipment. The reason that this is even lower, of course, is because firstly it's a simpler path, and secondly the only thing in that path is low pass filters with a 400 hertz cutoff. All the noise from previous stages is being filtered away.
Are you choosing a higher output on your low pass filter because of diffraction rolling around and it will equalize it out?
No, there is no equalization of drive units or of loudspeaker interaction with the cabinet in there at all. It is just a basic standard fourth order Linkwitz Riley plus the 2 time delay blocks. That is basically all there is to it. It's quite simple. There's no equalization because, you know, I don't know what to equalize and what kind of loudspeaker have I got. This is just to show the principle, really. Next. Right, now perhaps you don't think that's good enough, but the resources of electronics are not exhausted. Could we go back to the block diagram? I think it's about 3 back. There we are, right. Now you'll note I've got the time delay compensation at the end of each path here, which, you know, that was just how I did originally. I thought, okay, go forward back to where we were. That's it, that's fine. So I thought, hang on a minute, this is stupid. If I put the all-pass filters earlier in the path in front of the low-pass filters, then I can reduce the noise, because the noise from the all-pass filter will be removed by the low-pass filter, and it is. The mid-path, minus 110.4, goes down to minus 113.3. That's 3 dBs better just by rearranging the stages. zero cost. That's my idea of an improvement. You can't do that in the HF path because there aren't any low-pass filters in it. And you can't do that in the LF path because there's no all-pass filter to move. So you basically do that with the mid-path only. But 3 dBs for nothing, yes, worth having. Next. Right. So you think, well, I'd still like to get the noise down a bit. If we go back to our noise output of minus 100.9 for the input stage, you can say, right, okay, well, a 5532, that's a 30-year-old op-amp. It served us well, but there are quieter ones now. If you change the differential amplifier, in other words, the second bit in for the first stage, to a 4562, you gain 1.1 dBs, which is not a lot, really, considering that the op-amp is 10 times the cost, at least. If you change the input buffers to 4562 and put your diff amp back to 5532, that's a better way round. You've got 2 dBs better now. If you make the input buffers 4562 and put a double differential amplifier, which I'll explain in a moment, and make that a 5532, hey, 4 dBs better. Now we're cooking. And if you make everything a 4562 and have the double differential amp, almost 6 dBs improvement. But that is not free. That costs money. 4562s are expensive. Price is coming down, I'm told, but we've got a long way to go. Next. So I'll just explain the double differential stage. This bit is exactly the same. 2 buffers. This bit is exactly the same. Same resistor values, 560, 2K2. The only thing is it's miraculously grown a twin. There are now 2 amplifiers running off these buffers, and I combine the outputs through a couple of 10 ohm resistors. You have exactly the same gain, but you have 3 dBs less noise because the noise from these 2 is not correlated, and therefore it partly cancels. By the time you get here, you're down to minus 106.7. And this is where you get a 5.8 dB improvement. Minus 106 there, which is not a bad start. And after that, you're going to go into the path splits, you go into your filters. So it's 6 dB improvement measured here, 5 dB improvement measured there, because now the noise from this is becoming a bit more significant. It's always the way. You reduce the noise somewhere, and then the worst stage just moves somewhere else. It's like peeling onions, You're crying a lot. Okay, next. So if you do those improvements I've just talked about, the HF path is 4.7 dBs quieter. The mid output is 4.9, and the LF output, where we had a bit less scope for mods, is 2.6 dBs quieter. And the final figures at 114, 115, 119, I think you would agree, are not noisy. Next, we got another one? Yeah. I think this might be the last one. I'm not sure. Do we know how many more we've got?
How many more slides?
Yeah.
2.
2. Okay, right. I'll shut up in a minute. I promise. Okay. If we go back to where we were. That one, I think. Yeah. Right. Now this is an interesting one. This is. Since I wrote the book, I've been playing around with instrumentation amplifiers, and this is this configuration here, where you have a shared resistor and sort of gain there. And as you probably know, the great thing about this is that common mode gain is always 1. It doesn't matter how much voltage gain you've got, which is set by this, the common mode gain is always 1, and that doesn't depend on resistor matching at all. So if you've got significant gain in this stage, then you gain a common mode rejection improvement of the gain of that stage. This here is, I think I've set that for 12 dBs. Yes, I have, yeah. And so I get 12 dB common mode rejection improvement, always. It is bulletproof. It is absolutely solid. It does not depend on the op-amps. It does not depend on the resistors. These 2 don't have to be that well matched. That's an important thing. Now, they will affect the overall differential gain if they're out, but the common mode gain will always be 1. So then you go into your differential stage, which has now got unity gain, and you will find that is 4.5 dBs quieter than our original balance stage, without using 4562s, which costing an arm and a leg. So it's cheaper than 4562s. The common mode rejection is always 25 dBs better. That is absolutely solid. And it is, as I say, almost as quiet as the full 4562 version. Now you're thinking, well, this is a bit like perpetual motion. How can this be? Why is what's special about this? What's better? And the answer is that you've got it gained in your first stage, and so the signal level has been up. It's been brought up before it hits the second stage. So the second stage has much less scope for degrading the noise. Right, one more? Is it? Well, yeah, that's it. So I'll hang on a second. I'll just do questions in a moment. If you want to look up more about this stuff, I will be putting it on the website, douglas-self.com. And this is my email address. If there's anything you want to talk about or comment, then feel free to do so. Right, questions?
So was it you in a measurement, I read a while back that thought the 4562s had a common mode rejection issue themselves?
It wasn't me, no. Right. As far as I know, they're fine.
So if you make that last circuit that you had there with the 532s without 4562s instead, what would be the...
Well, that will be quieter again. I mean, I haven't actually tried that.
Okay.
I would have thought, it's hard to say, I doubt if you'd get more than a couple of dBs, and it would cost you.
You talked about linearity with resistors a little bit. They're not that unlinear.
Yeah.
But what about noise level with resistors? Is there particular types that you prefer over there, it's like polypropylene over polystyrene, or not?
Well, not really. I mean, all resistors these days, or virtually all resistors, are metal film. And they effectively have no excess noise. I mean, you just get the Johnson noise that you would get from any resistance. If you don't get excess noise unless you start using carbon film with voltage across it or something like that. And people don't do that anymore. Not even in the cheapest of hi-fi amps. I don't think you see carbon resistors anymore. So that's basically a non-issue. Yeah.
Yeah, I was wondering, if you're trying to keep a pair of speakers down to about $5,000 with what you've got up there, it would seem that these new small Class D amplifiers would work pretty well. What's your opinion on them, and do you have any favorite Class Ds in this line?
Not really. I mean, I've done work on Class D amplifiers, but it's very small amount compared with what I've done on Class A and Class B and so on. So I don't regard myself as an expert on Class D amplifiers at all. I would say I am emotionally scarred by them. Because the last company I worked for, which is the company that makes stuff for the Richer Sounds chain in Britain, which is a very big hi-fi chain, they committed themselves to using TriPath Class D chips. Now you're probably all aware of what happened to TriPath. This is the problem with Class D. I mean, you either have to design it yourself, which is a real major pain because you've got to become an expert on a very obscure and very, very difficult kind of technology, or you've got to buy it in from somebody. And if you buy it in from somebody, then, if they disappear, you're screwed. And we were, I can assure you. We did a last time buy, we got the last ones in the world as far as I'm aware, and after that, we just had to drop the product. So I'm kind of not that keen on Class D as a rule. It's kind of, it's bad memories. But I'm trying to move on. Any more?
Yeah, you were saying about having DC offset problems in power amps in tri-amp systems.
Yeah.
And for tweeters, it's not so bad to get a reasonable capacitor. It's going 50 microfarads of polypropylene, not so bad.
Yeah, and expensive.
Mid-range.
Expensive.
Yeah, some of us have a little bit of money.
Yeah.
But the problem is that if you want to do it with mid-range, then you start getting to hundreds of microfarads.
You talk, yeah. Yeah.
However, have you thought of parallel inductors? So
Well,
the amplifier is going offset. What
yeah.
you do is that you hope the thing doesn't burn up before the fuses go.
Yep. Well, aren't you going to need a pretty hefty inductor to make sure that it doesn't sort of, load the feed to the mid-range? Because that's going to have to be probably an iron core inductor. It'll distort.
Well, if it's a parallel, the distortion's really consequential.
Well, if it's a good low output impedance from the power amp, then yes, that should cope with that. It's a possible idea.
Yeah. Because what happens is also you don't really need to worry about the thing distorting because are you familiar with PV amplifiers?
I'm vaguely aware of them. I'm not that familiar.
Well, they're not the best sounding amplifiers, but what they did have, they had a very clever little offset protection circuit. They had a triac on the output.
Oh yeah.
That was exactly, you see where this is going.
Now we're going back to emotional scarring here. Yeah, and you're bringing back bad memories. When I Yeah, well, when I first worked for Cambridge Audio, we designed, this was back in the days of the P60 and the P100 and things like that. I mean, this is 1975 or thereabouts. The technical director thought that would be a cracking idea. You know, we would put a triac across the output and we would fire it when things went wrong, and then that would be fine for the loudspeakers. Well, maybe. It was pretty bad for the amplifier. You need a really big triac if it's going to work more than once.
Well, what happens is that they just sacrifice the triac.
Well, yeah, but you also sacrifice the PCB tracks and the power supply, and we sacrificed pretty much everything, really. We had to destroy the amplifier in order to save it, you know. Well, I can't imagine. I know Quad did that at one point because they got in trouble with their current dumping thing, and they forgot to put in DC offset protection. They put that in, and no relay, you see. I think the only way you can do this is with a relay. It's a pain because they're expensive if they're going to work well and work more than once, you know. But it's the only reliable way.
Yeah.
Okay, any more? Any more?
Okay.
Right, okay, I think we're done. Right, thank you for listening. Now, I have just 2 copies of the crossover book with me. These, I understand, are $61 on Amazon. I'm prepared to knock these out for $50 if anybody's interested. Only got 2, first come, first served.
Would you like to sign?
I certainly will, yes. I'll be happy to.
And last year, Sigrid Linkwitz talked to us, and we had
I've gone through it once already, and
Yeah?